thanks very much. Okay, so yesterday, at the end of the lecture, we arrived to this recipe on how to compute the phase equilibria for this generalized non-equilibrium harmonic description of scalar phase separating system. I insist on the fact that this is a deterministic equation. So this is a recipe that tells you if you know that what you can do, but if you had noise here and you wanted to take the average, you have a bunch of nonlinear functions, so you would have to compute a renormalized harmonic equation before you can apply it and use it. So how does the recipe go? You look at these gradient terms first. You introduce this function r, which is defined by this ordinary differential equation. The second derivative of r with respect to rho is minus 2 lambda plus kappa prime over kappa times the first derivative of r with respect to rho. In the equilibrium case, when 2 lambda plus kappa prime vanishes, then you get r double prime is 0, and the solution of this equation is simply r equal rho. Now, then you look at the local part of your function g here, and once you've solved that, you have r of rho. You can invert it, and you get rho of r. And so these, you can rewrite it as a function of r, and you can integrate it with respect to r. And you define this generalized free energy phi of r. And then the condition that your coexisting densities have to satisfy is the equality of this generalized chemical potential. The derivative of the free energy is the same. And the equality of pressure, which you can read as this common tangent construction. Okay. So let's see how this works in a practical example. Okay, and the system I want to discuss. Okay, so one more statement. So here I gave you the kind of, I gave you the way of deriving method, which is the way that we used to find it. We're trying to make this Newton mapping, and we realized that we could solve the problem that way. But there is a deeper reason why it works, is that in equilibrium, your harmonic equation can be written like that. Now, with the function r, you can take your d-dimensional harmonic equation and rewrite it as rho dot is equal to the divergence of a mobility times the gradient, not of delta f with respect to delta rho, but of the functional derivative of a generalized free energy h with respect to delta r, where the expression of h is given here. You have a local part and you have a gradient term. Now, because here you have rho dot and not r dot, h is not a Lyapunov functional, so it's not strictly decreasing as function of time, as opposed to f here, which is a Lyapunov functional. But still, in the steady state, this guy is extremalized by the dynamics. And one thing I mentioned in passing, because of a question of one of you yesterday, is that if now I'm looking at this 2D problem when I have a droplet will have a finite curvature radius, and I can use the gradient term to compute the Laplace pressure-like correction to the binodal in infinite system, and it works pretty well. Okay, so let me apply it to a model. Now we know how to do that for particles interacting with pairwise forces, thanks in part to the work of Ahmad Omar and his group. But it's a longer computation, so I'll go for the simpler system. Which I will reuse in a second, which is a system inspired by what happens in bacteria, which is what we call quorum sensing self-propelled particle. Now, if you think about yourself walking in a crowd or bacteria swimming in a fluid, you don't interact with people by colliding into them. No, the first thing you do is you see them and you adapt your pace to the density around you. So pairwise forces, that's a model that physicists love, but it's not so relevant for active particles. And what's much more relevant for active particles is sensing. And quorum sensing is when you make parameters of your model depend on the local density that you measure around you. So imagine that you're at a position Ri, and you say that you have a kind of coarse-graining kernel with which you will sense the presence of particles around you. And so you define this effective density field as a sum over the neighbors of k of Ri minus Rj. If k was the delta function, this would be my empirical measure up to normalization. But here I'm allowing for some finite range sensing. Okay, and that, for instance, would describe what happens when you have bacteria that swim. If you have lots of other bacteria around you, they eat your food, you have no food. If you have no food, you cannot swim. So these type of interactions are very natural for bacteria. Okay, and we can look at what happens if you have diffusivity, if you have tumbling rate. In this model, if V is a decreasing function of rho, you get motility-induced phase separation. And I will show you now simulations. Okay. So here, on the left, you have simulation of active Brownian particles, the one that do continuous rotational diffusion. On the right, you have run and tumble particle, the one that goes straight, turn at random. They are interacting with this V of rho. Each point is one particle, and the color code is the local density. And I'm showing you a large-scale picture. And I could have swapped the label, and you wouldn't have been able to tell me what is what. And this is a form of universality that at this scale, at this macroscopic scale, the microscopic dynamics of this particle is irrelevant. What matters is that they slow down with density and that they are persistent. And you get this phase separation with the creation of this dense droplet. So here the particles are very slow, and here they would be much faster. And so the question is, okay, can we build the hydrodynamic description of this model? And can we use the recipe to predict the phase diagram? Okay, so how do we do that? It's pretty easy for this system. On the large scale at which you have, on the macroscopic scale at which you have phase separation, the particles have done a lot of run and tumble, so they've randomized their motion and they're effectively diffusive. So you can approximate these by a Brownian random walk, complicated one, but you can do that. And then you can use stochastic calculus, Ito formula, to build the fluctuating hydrodynamics. Then you take a mean field approximation, and that gives you a hydrodynamic equation. And if you look at this hydrodynamic equation, it is of the form that I announced. So you get a mass conservation equation. Rho dot is minus divergence of a current. The current has a mobility, which is the density times V square over essentially the persistence time of your particle. And then inside the gradient, there is a part which is a functional derivative of a free energy density, so a local part of the free energy density. You have one contribution, which is this rho log rho minus 1, which is just minus the entropy. That's the number of microscopic configuration of particles that will give me a given density profile, rho of r. And then I have the equivalent of an energy term, which stems from this V of rho, but which is very weird because it's this integral of log of V of rho. And in addition, I have gradient terms that I can also derive. These gradient terms are not the derivative of free energy. In the language before, this is minus kappa, but there is no grad rho square term, so there is no lambda. So 2 lambda plus kappa prime is not 0. So if you extremalize f to get the phase diagram, you predict a phase diagram which is wrong. Okay. So can we apply our recipe? Yes, we can. We can rewrite the dynamics like this. G has a local part which is simply log rho plus log v. And then the gradient terms have just the kappa term. And there is no lambda. I can solve this equation. I get R of rho, but I don't get a simple R is not equal to rho. It's a much more complicated function. And I can look at a case in which my V of rho is decreasing, so that I know I have phase separation. And I can build my free energy density by integrating G naught with respect to R. And when I do that, I get something that looks like this for the parameter of the simulation before. And I can try to, and I can build this common tangents construction, measure the gas density, measure the gas generalized density, the liquid generalized density. I can invert my R of rho relation and get the binodal. And here on the right, what you see is the density of coexistence as V gas over V liquid is varied, meaning as the height of this drop in velocity is increased. So the symbols here are a bunch of microscopic simulations in 1D and 2D, on lattice, off lattice, with run and tumble active Brownian particles. You see again this universality I was talking about, that which is the fact that the hydrodynamic equation is very robust, and you see that all of them give you the same coexisting densities. In black, you have what you would get if you ignore this and simply try to do an equilibrium construction. Qualitatively, you're right. You predict phase separation. The phase diagram has the kind of correct general shape, but the values of the coexisting densities are wrong. And if you do this our theory, you get something which is much closer. And the reason why there is a small discrepancy is because to get there, we have neglected higher order gradient terms, and these higher order gradient terms would matter, and so that's an approximation, and that's why this is not fully exact. Okay, so one of the questions is that I'm telling you this is because of the gradient terms. You could ask me, are you sure? And the answer is yes, because I've worked with Thierry Bodino and Clément Erignou, and we use the lattice model for which you can construct the harmonic equations exactly. And for this model, we could apply the methods, and then you get a phase diagram that match, which is exact, which match exactly the simulations, unsurprisingly. So there are some systems which are a bit more complicated, but that can be used to solve the same method. But I will not enter into detail for the sake of time. Okay. So let me recap what I've told you so far yesterday and today. Anytime you have a feedback between getting denser and going slower, you will have this motility-induced phase separation. You can have this motility-induced phase separation. This is very generic. This is something that you get with any type of active random walks that has been seen in a bunch of systems, in also many experimental systems. If you're able to build this generalized canne-Hilliard description, which is difficult, then you can predict the phase equilibria using these generalized, this change of variables in this R variable. There are some models for which we have exact solutions, which is always nice because that guides us into the darkness of non-quantum physics. But there are still many open questions, and in particular, yesterday somebody asked me about the voids inside these dense droplets, and I think that there's lots of interesting physics that still has to be understood. Phase diagram is the first thing that you want to describe in the system because that's what's new. What's new is not the existence of a critical point. The critical point, we believe, is of Ising universality class. But the fact that you have this phase separation is new. But there are lots of other questions you can ask. What about nucleation? What about the pathways? What about transition paths between homogeneous and phase-separated systems? How do they differ from equilibrium physics? And this has been barely brushed. Now, I'm very happy with the theory. It's a new collective behavior. We understand everything. But it's very sad that I'm only able to do that for lattice models or this particle-based simulation. And I would really be able to tell you, okay, this has an impact and allows us to understand something. So there is a question that as a physicist, theoretical physicists, we always feel a bit worried about is this just a game I'm playing, or can I learn something about a real system using that? And I want to spend the next few minutes discussing application to the self-organization of bacterial colonies. And this is a joint work that started with that has joint work with Jiandong Huang. That started because in 2010, I was in a conference in Korea. It was like one of my first invited talks in an international conference as a postdoc. I'm speaking in the afternoon, so I'm not really focusing on the talks in the morning. And there is this guy who's giving talks about pattern formation, and then he starts to show my theory in his experiments. And I was like, if this has been published 3 years ago, I will really sound like a fool this afternoon. Fortunately, because we had done just the theory, we were first and they came a bit after. But then we chatted and then we did this second work together. Anyway. Okay, so what did JD did? He took bacteria, and bacteria have these genetics. Bacteria are wonderful. You put DNA into them, and then they express it. So it's very easy to, very easy. I mean, you can manipulate them and make them do a lot of stuff. So this is a cartoon of a bacterium, and you put 2 pieces of DNA inside, those called plasmids, and the first piece of DNA codes for some signaling molecule that go through the membrane and diffuse in the environment, and then it can go back into the same bacterium or other bacteria, and it will regulate the expression of another gene. And here the gene which is put under the control of all these is KZ. What is KZ? KZ is a gene that codes for a protein that takes a bacteria who is tumbling and tells it start swimming. So if I give you a lot of KZ, you don't tumble, you just swim. If you don't have KZ, you spend your life tumbling, you're not swimming. What's the result of this? The result of this is if you're at high density, you have a lot of AHL around you, and so you don't have KZ, and so you don't move. Okay, so that's your essentially V of rho. You're not at high density, you're not moving. While at low density, you're happy, you have very little AHL, you have a lot of KZ, and you can swim. They can quantify that experimentally. They look at the large scale diffusion coefficient of the bacterium as function of the cell density, and you see happy, 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 unhappy. Okay, so it's essentially motility falls. I look at that and I say, you'll have MIPS in your system. So they do an experiment, a standard microbiology experiment. You put a few microliters of your bacterial concentration in the center of a Petri dish. You wait for a day, and what do you see? Not MIPS. So there is something which is nice, which is you see something, but instead of saying the phase separation that I predicted, instead the system self-organizes into concentric rings of finite size. Okay. So I'm half happy. I'm happy because part of my theory is there, but I'm sad because I'm missing something. So the first reason could be that I was playing with this V of rho and instantaneous tumble, but I told you that KZ actually regulates the duration of tumbling, so maybe my model was wrong. Maybe I should look at another type of interactions. So I can take a model of run and tumble bacteria, which is a bit more complicated. I have bacteria that can be in two states. They can be in a running state at speed V, and they can enter at rate alpha a tumbling state where they're just randomizing their orientation. And then there is a finite state at which they go back into running. So there is a finite duration. I can redo the computation I did yesterday on the board about the steady state when you have these rates which are position dependent. We had, if you remember, rho that was 1 over V, proportional to 1 over V. Here, in addition, we have this TR plus TT, tau T over tau R. What is this guy? It's just the fraction of time that you spend swimming. So this is just one of your average speed if you average both the swimming phase and the tumbling phase. So the same type of physics. So I don't expect something very different. So this is just MIPS in that model. I do microscopic simulation of my run and tumble system. So Anise Curatolo did that. And that's the case in which the speed goes down. So that's what I described before. And I'm showing you 3 different time snapshots. When I have done 1,000 times this cycle between running, tumbling, and running again, 10 to the 4 or 10 to the 5, typical scale would be 100 times the persistence length, the speed times this persistence time. For bacteria, this is 10 micrometers, so this would be millimeter. And what you see as time goes on is you see coarsening. Okay, so maybe if instead of having V prime of rho, you take this tau that depends on the density, like in the experiment, you see something different. So you can try to play with longer tumble. At high density, my tumbling time is longer, so I spend more. I don't move at high density because I just tumble longer. Same thing, coarsening. Maybe the frequency, the duration of the tumble should not change, but it's the frequency which can change. So now what I will be doing is I'll have more frequent tumble. And then, again, same thing, coarsening. So, again, we are facing this kind of universality I was talking about, that always leading to motility reduction are qualitatively equivalent, and they lead to motility-induced phase separation. So,
yes. And should you let it run longer, you would get the same bubble as you showed before.
Bubble or a stripe, depending on the density. Yes. You had also a question? Oh, okay. So
Julien, because it looks like you're in the spinodal region to begin with.
So here I was in the spinodal region. If I had been in the binodal region, I would have seen nothing, 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 boom, nucleation and growth. Yeah, you can see both of them. Okay. So what's missing? Well, what's missing, you can read it here. Tau for bacterium is 1 second. 10 to the 5 tau is 1 day. The division time of E. coli is between half an hour and 1 hour. Meaning that, here when I'm doing my simulation, I'm missing an important ingredient, which is that the bacteria divide. They don't just swim. So let's look at what happens if I take my model for run and tumble particle that does MIPS and I add population dynamics. How do I do that? I take the model, I told you that we can coarse grain this system into harmonic equations. These are the harmonic equations. So you get rho dot equal div. These I could rewrite it as mobility times grad g, but I like it a bit better here like that. So I have this kind of large-scale diffusion constant times grad rho. So it's a d grad rho. So this is a stabilizing term, right? It always makes any density fluctuation go down. But then I have this second term, which is a drift term, because you see it's proportional to rho. And it's proportional to the gradient of v times these alpha over alpha plus beta. And alpha and beta are these rates to enter tumbling or enter swimming. And what this is a drift that tells you go towards region where you're slower. So that's the term that's destabilizing. So if I make it something denser and you're slower here, this will take me go up gradient. Then I open a book on mathematical biology, and Murray tells me that if I want to add population dynamics, what I can do is essentially add a logistic term here. So I have my MIPS without a minus sign. That should be a plus. And then I simply add this term. What does this term do? When rho is very small, I can neglect the second term. I just have exponential growth. Rho dot equal mu rho. And then when the density is getting closer to rho naught, bacteria are running out of food. And essentially, the division rate, mu, goes to 0. And beyond rho naught, bacteria would lack food, and they would stop running, stop moving, and stop doing anything. Now, if I just look at the logistic equation, this is a well-known equation, and it has two fixed points, rho equals 0 and rho equal rho naught. And the stable fixed point is rho equal rho naught. And so essentially what this guy is trying to promote is a system homogeneous at rho dot. Because there is no gradient, if you think in terms of Fourier space, when Q goes to 0, so at large scale, the gradients are irrelevant. So this guy really stabilizes the long wavelengths of your system. On the other hand, if you look at small length scale, the gradients are important. This guy dominates, and MIPS destabilizes small length scale. And the computation between the two selects for a finite wavelength. And if I put that in a computer and I simulate it, these are the snapshots you see. You can see here what's called a Fisher wave ahead of the colony that's spreading out. And then in the wake of the Fisher wave, you get the formation of these concentric rings, which qualitatively accounts for what you see in the experiments. So let's recap. The Coulomb sensing interactions lead to density-dependent motility. As argued, this leads to motility-induced phase separation. And then this couples on longer time scale with population dynamics, which stabilizes large wavelengths, and the competition between the two leads to a finite size pattern. This is a very simple mechanism. It doesn't require fine-tuning, and that's why you can do stupid model in your computer, and it works fine when you compare with bacteria in a petri dish in which you have lots of other complexity, because this is very robust to modification that you do to your system.
Predict this size?
So you can do amplitude equation on the patterns, and for the parameter region where your amplitude equation works, you can predict So on the second paper I will be speaking about, we were describing patterns with two species, and I insisted that we will not make a quantitative prediction for the experiment because I have absolutely no faith that our simple models quantitatively describe experiments. I don't think you should compare our theoretical physics model with quantitative experiments. Of course, a referee wanted a number. So we said, okay, you can look at the peak of your the fastest growing wavelengths. How does it compare? We are within a factor 2 with the experiments. So but if it had been 28, for me it would have been the same thing. So you can understand the physics. The competition is simple to understand. Is that this term here, this is a volume term, because you're creating mass everywhere within your system, while this is a perimeter. These are surface area terms, because it just flux through the boundaries. So you want to balance something which is a volume effect with a surface effect that selects a length. And I can detail that on the board if you want. But of course, estimating the precise value of this flux is difficult beyond the amplitude equation regime. So when the transition is subcritical, yes. Okay. So can we look at more complex ecosystem? Okay, so first other question, yes.
So I guess for liquid gas phase separation, you can always move to a grand count ensemble in which particle number is fluctuating and you still have a phase transition. So does there exist a MIPS model with non-conserved particle number that does MIPS?
So we don't have, okay, so for me that's been a long-standing question that's been in my head. We don't have ensemble equivalence out of equilibrium. So if you ask me how do you build a reservoir for that system, I don't know. Actually, I know a little bit for this model because I know that the chemical potential is rho times V. So I can have a game in which I add or remove particles, imposing the chemical potential, rho times V, instead of just, But if you just add and remove particles that concentrate as you would do in a grand canonical ensemble, you don't get, you don't get, for instance, the collapse of. So if I look at my phase diagram. And I replace this rho by mu, a chemical potential, this will become a line with a critical point at the end, right? If I do that with just alpha and beta rate at which I add and remove particles, I would get the same thing. I don't collapse these regions. So we don't know how to build grand canonical ensembles for active matter systems. That's something I've been wanting to do for a long time. Now that we know a lot about the pressure, I would like to be able to do the same thing with chemical potential, but we don't know how to do that. That's an open question. Any other question on this part? You had many questions yesterday, that's nice.
Yes. I mean, you could get the same pattern from sort of maturing. I mean, essentially.
Thanks very much. Please ask this question again in 6 minutes when I will have something that you will want to call it Turing, and then I will tell you why it's not Turing. But yes. Okay, so can we, it's nice to be able to talk about experiments and unexpected for me. But this is a very simple idealized system, very well controlled. So can we go toward more complex ecosystem? So we can, and to do that, one thing that we need to do is to increase the number of bacteria that live together. In your guts, you have something like 200 bacteria that coexist. So we did the first work that I will describe now about what happens when you have two strains. And we've recently done another preprint on the large N case, but I don't think I'll have the time to talk about that also. Okay, so how do you look at mixtures of random tumble bacteria interacting via quorum sensing? I will consider two strains, which I will call two species of bacteria because there are no biologists in the room. And I will denote them by alpha and beta. And I look at several types of interaction between them. There can be self-regulation when the speed of alpha depends on the density of alpha and the speed of beta depends on the density of beta. There can be cross-regulation when the speed of alpha depends on the density of beta or the speed of beta depends on the density of alpha. There can be global motility regulation when the speed of alpha depends on the total density. And then what we'll be looking at is both activation and inhibition of motility. So far, I only talked about inhibition of motility because activation of motility doesn't do anything interesting when you just have one species. And we did essentially three things to understand the physics of these systems. We did numerical simulations of microscopic models, analytical coarse graining of the dynamics and study of the field theoretical description, and synthetic biology experiments. And this was done using the bacteria engineered by Jiandong Huang and a setup that was built by Adrien Daher at MSc in Paris and with the help of Yongfeng Zhao. Okay, so let me first do some theory and let's look at what happens. So the first type of interactions we can look at are what I will call symmetric interactions. I'm not saying reciprocal because they are always microscopically non-reciprocal interaction, but symmetric. Because it gives me a rich physics, I will look at what happens if you have self-inhibition. So you produce some waste that's toxic to your peers, but global activation, that you also produce some stuff which is beneficial for everyone. And the way I'm modeling that is by saying that each of my species has its own bare speed, and then two sigmoidal function that makes the speed either go down or go up as some density varies. So here it goes down as its own density increases and goes up as the total density increases. That's the phase diagram you get if you put this in a computer and just run it. So I'm varying the density of species alpha and the density of species beta, and I have 4 different phases. In white, you have boring homogeneous system. Nothing's happening. Your system is homogeneous, well mixed. Okay. In red, you have what I call single species phase separation. Why? Because if I start at this blue star, my system phase separate along this tie line. And if you look, so I have coexistence between that point and that point. You see that vertically they are very close for alpha, meaning that if I look at the density field of alpha in space, I see very mild modulation. But they are very far from each other in beta, and indeed rho beta phase separate. So essentially what happens is rho beta phase separates, and because they're coupled, alpha reacts a little bit. So essentially this is a bit boring, because just with n equal 2, what happened with n equal 1. Now, more interesting, there is this green region where my tie lines now is the line y equal minus x. What does it mean? It means that rho alpha plus rho beta locally is constant. So if I look at the total density, it's uniform. So I don't get this type of modulation. But locally, the composition varies. I have alpha-rich regions and beta-rich region. And so what this is demixing. Globally, if I look at these systems with dark field, I would see a uniform density of bacteria. But if I look at it with fluorescent labeling of my bacteria, I would see red and green patches that would be distinct. Even richer, there is this yellow region here, there are 2 of them, in which you get triple phase separation. So you get coexistence between that point, and that point. And here what happens is that this line is on y equal x. So this is a well-mixed high-density point. This corresponds to this white region where rho alpha is equal to rho beta, and they are indeed dense. So here, that's the total density field. You see a global phase separation between dense region and dilute regions. And in addition, a demixing in the dilute region, because the dilute region are only alpha-rich or beta-rich. So essentially, when the system is dense, everybody cohabits happily, but when the system is dilute, they phase separate. Okay, so a very rich phenomenology. And you could ask, well, you were able to do this theory with your variable R. Can you, explain this using some form of generalized free energy? And the answer is yes, in this case. We don't even need the R function for the case of symmetric interactions. And we can build an effective equilibrium description. So the idea is that we do the coarse graining of the microscopic dynamics, again using diffusive scaling. We again have the same type of model. And the fluctuating hydrodynamics that we get look like coupled generalized model Bs. So the density of species mu satisfy a conservation law, so minus divergence of a current. This current has a noise part, so there is a Gaussian white noise field here with a variance, which is given by this function m mu here, which is the density times the large scale diffusion constant. And the deterministic part is nice because you have the same mobility times the gradient of some kind of effective chemical potential u mu. And if you look at this chemical potential, you get again this log rho plus log v, which is log rho v, which is the same thing as what you had in the one species case. Now, because you have cross-regulation of motility, this encodes interaction both between species, I mean within the species and between the species. Okay. So let's try to understand this equation a little bit. The first thing that I'd like to show is that log v here acts as an effective energy, as the derivative of an effective energy. And if you think in terms of chemical potential, when v is small, log v will be very negative. When v is large, chemical potential will be very large. You know that you get flow from high chemical potential to low chemical potential. So this tells you that a slowdown corresponds to attraction, while a speed up corresponds to repulsion. So you expect, you have a way of reading these quorum sensing interactions in almost like effective forces, which will be useful to understand how we get the patterns afterwards. The second thing is that if I look at this model, there is nothing out of equilibrium in this fluctuation. So because I have this Stokes-Einstein relation between the mobility and the amplitude of the noise, the fluctuations are bona fide equilibrium fluctuations. This is an approximation or a mistake due to this diffusive scaling. The real noise should not be Gaussian, and then there should be, to higher order corrections to that. But to this level, it's fine. And so the question,
one question. So at the first lecture, you didn't add a noise, and you could study everything straight from the deterministic thing. To see pattern formation, the noise is important.
No. The next thing I will do is mean field. So no. I will take the average and I will assume that mean field works to get the phase diagram. Yeah. So you don't. Yeah. So essentially this is the same route as the one I followed before, and then I did one more step, which is take the average of this function and assume that the average of the function is the function of the average, and I will do it here also again. But what I wanted to show here is that this route gives you a noise, which is a nice noise, even in the many-body case, because you have the same mobility here. So if I can write mu as the functional derivative of a free energy, then I really get an equilibrium system. Okay. So you can ask, does this happen? And what I told you yesterday is that for this to happen, you just have to satisfy your Schwarz condition on this functional derivative. It's more complicated for n species. This is the work of Jeremy Auburn, by the way. So what you need is the functional derivative of u mu with respect to rho nu r prime to be equal to the fully symmetrized one. So the functional derivative of u nu at r prime with respect to delta rho mu of r. You can take this and you can inject it there. And if you make a local approximation, meaning that this v mu, you don't say that it's a functional of this field, but just a function of this field, then the condition to get a free energy is that the way the log of my speed vary when your density changes has to be equal to the way the log of your speed vary where my density changes. So this is a very weird relation that I don't know any way of guessing that from microscopic, but it holds for the choice of function that I chose on the previous slide. And so when you have that, you arrive at a free energy. You know that in this case you have a bona fide free energy. You're happy. You can extremalize it, minimize it, and predict the phase diagram. And here it's a comparison between the simulations in black and the predictions of the free energy in color. And you see that they match very well without any fitted parameter, which was a big surprise for me, because when we do this at this stage, we neglect the gradient terms. And so if I wanted to extend that with the gradient terms, I could, but then I would need to use this type of R variables. And in the single particle case, this leads to significant shift of the phase diagram. And here, probably part of these discrepancies due to that. But essentially, the local effective equilibrium theory works very well. So this is a case in which you have your microscopic model with n species, you coarse-grain it, and you're able to predict analytically the self-organization of the system. So in one hand, it's nice because we are able to predict what we see in the system, but it's also a bit sad because I try to sell you active matter by telling you it has amazing new collective behaviors that you don't see in equilibrium, and I'm telling you can understand it with a free energy. So from a control point of view, it's nice. From a physics point of view, it's not as rich as could be. And so you can decide not to look at symmetric interactions. You can look at asymmetric interactions. Yes, one thing I wanted to mention is that if I had an equilibrium model with pairwise forces, this condition would be action-reaction. I would need that Fij is minus Fji. And so these you can look at it as a generalization of the action-reaction principle in quorum sensing mixtures. And it's weird. Anyway. So the other thing I can look at is asymmetric interactions. And so we keep this self-inhibition, which is nice because it creates patterns very easily. And then we look at opposite cross interactions. So for instance, we'll have alpha enhances the motility of beta, and beta inhibits the mobility of alpha. So if you remember what I told you, inhibition of motility is like attractive forces, but activation of motility is like repulsion. So there is a bit of, how do you say, incompatibilities between these two interactions. And indeed, this can generate a run and chase dynamics. So maybe I can show you a movie that corresponds to the one on the right. So here you see that you have these kind of waves of one species, blue or red, which are being chased by the other species. And you can have it either in the form of this chaotic sea of bands here on the right, when the system is strongly anisotropic, and when you have a weak anisotropy, you get this macroscopic band. And so here the blue is being activated by the red, so it's going away from it. And the red is being slowed down by the blue, so it's kind of accumulating what it is and catching up with it, which is very counterintuitive. Okay. Is this relevant for experiments? Yes. So Jiandong Huang can, instead of taking one bacterium and modify it, he can take two bacteria, two strains. So he starts from the same strain of E. coli, tag one of them in red, the other one in green. And then he puts a bunch of plasmids in the bacterium. So the red bacteria will produce some molecules that will go and regulate the mobility of the green bacteria. And in this case, this is activating Key-Z, so it's helping green bacteria to swim. Conversely, the green bacterium is producing this signaling molecule that goes into the red bacteria and enhance Key-Z. So you can also, So essentially you get, in this case, a density-dependent activation of motility, because if I'm green and I have lots of red around me, I have lots of these molecules, and I have lots of Key-Z, and conversely. You can also do inhibition of motility. You can do whatever you want. Okay, so this is the experiment built by Adrien Daher. You have two light paths to record the fluorescence of the red and the green bacteria. This is Yongfeng Zhao playing with the setup, and you have this rotating plate so that you can do 6 petri dishes at the same time. You seed a well-mixed colony at the center of your petri dish. You wait for 1 day. Mutual activation of motility, that's repulsive interaction. Again, you see the formation of these concentric rings here. And you see that they are demixed in phase opposition. Okay. These are just, that's the result of the experiments, and these are just the corresponding channels shown separately. And then you can also do mutual inhibition of motility, and in this case you also get rings, but the rings are colocalized. Again, you get rings and no phase separation. I would argue that this is due to population dynamics, and we can show it. And that's when your question about Turing pattern will be relevant. So we have two strains, two species, Rho A and Rho B. We have these logistic terms, so they are both growing exponentially, but they're competing for the same food. They're clonal, so that they will be saturating. We have this quorum sensing interaction that gives us this transport term, and we put that in the computer, and we reproduce that if you have mutual activation of motility, you get demixing and the formation of rings. Mutual inhibition of motility, you get colocalization. So that's, again, this kind of general principle that the quorum sensing interactions, the motility regulation promotes phase separation, and the population dynamics arrest phase separation. And now I can address your question. So there is another way of getting this type of pattern, which is called Turing pattern. In Turing pattern, what you do is you have boring diffusion. So you have just here dA Laplacian Rho A, and here dB Laplacian Rho B. And you would have fancy reaction terms. You would have one that activates the other one that inhibits. And if you fine-tune your parameters, you can get this type of rings. Here, the situation is converse. The population dynamics is boring. It's just promoting something uniform. And what's promoting the interesting physics is the quorum sensing interaction. So I would say it's the converse of the Turing pattern. One of the things which I like a lot about this, that Turing pattern doesn't have, is that this is super robust, because I don't need to fine-tune anything to get that. And to go from here to there, it's not that I change D from 0.04 to 0.08, it's that I change a sign. Instead of activating your motility, I inhibit it. So I think this is a much more robust, from my limited experiments with simulating Turing patterns, which was painful. I think this is a much more robust pattern formation. It took, I don't know, 60 years for biologists to find experimental realization of Turing patterns, because this is difficult also, I think, because it's fragile. I think it will take also a very long time to find that in nature without engineering it, because measuring the motility of things in biology is amazingly difficult. So we just submitted a paper with Alberto and Ada on this random modulation of motility, and one of the comments we had was, oh, but motility regulation is not important in biology. We've never measured it, and it's an interesting way of thinking about things. But so anyway. Okay, so I don't really have the time. You can go to high-dimensional ecosystems, do the same kind of things. There would have been a connection with random matrix, but I think I will jump over that. Yeah, big figures. There is a Wigner semicircle. That's, you'll have the slides, so you'll be able to look at them. Okay, so just let me conclude this kind of first half of my lectures. Motility-induced phase separation and population dynamics lead to pattern formation. I hope I've convinced you that it's a powerful self-organization pathways for self-propelled agents. I've shown this in the context of bacteria, and it can even make contact, almost quantitative contact with experiments. You get these nice traveling patterns that we haven't seen experimentally because they have not engineered the asymmetric interactions, and that's something that we would really like to do. And in high-dimensional ecosystems, you have also very nice phase separation. So I hope that this convinces you that scalar active matter is already quite rich, and just wait till the second half of the lecture when now we put aligning interactions and things become even more complicated. So I think that this is where I switch. So if you have questions, probably I can take them now, and then I will move to collective motion, which will be a slightly different topic. Yes.
Maybe just correct these traffic patterns. Maybe I missed something.
Yes. I have to jump over these slides, which are super heavy because of the. Yes.
Okay, so can you explain how this related to what you?
Okay, so what I have here is I have two species of my run and tumble bacteria. One is, and so each bacterium is measuring the local density of its peers and of the other species. And species beta is being slowed down by itself, but it is being sped up by species alpha. Species alpha is slowed down by itself and by species beta. Okay. So they do their random tumble walk. You coarse grain them, you get two coupled, essentially model B, non-equilibrium model B. And these have instabilities that lead to the formation of bands that kind of colocalize and travel together.
Okay, and this is something that you can prove from the equation?
So what you can do in this system, you can do linear stability analysis. You can show that you have imaginary eigenvalues, so you get traveling waves. I think that there is a paper by, so for this system, the problem with is that this guy is horribly nonlinear and pretty hard to study. But what you can do is you can make weakly nonlinear expansion of that, and you get what's called non-reciprocal coupled model B, or coupled caniliard. And Giulia Pisegna has been working on finding analytic solutions for these coupled traveling waves. And I think that they have something. I haven't checked it, so I don't know. We looked a little bit for, I'll show you this afternoon how we looked at these traveling profiles in another context. And when we tried, we failed. But it seems that people now have worked it out. So this, yeah.
The other picture, you can
so,
something about?
No, this we don't know at all. So essentially what happens is that this is in the case in which the asymmetry is very small. While this is in the case in which they're strongly asymmetric. So one is very strongly enhanced and the other one just a little bit. And why you get this finite size instability is also something complicated. I don't think that with this level of description you can predict it because we're missing gradient terms. So here the only instability you can have is a Q equals 0 instability, while this is a finite wavelength instability. So Benoît Mao, who's just been hired in Montpellier, has been trying to generalize this to retain higher order gradients and not stop at order grad square, and then you can generate finite Q instability. Yeah, so I think you can, you kind of can do that by doing Boltzmann type solutions where you have a zeroth order equation that would be that, and then you try to find a first order correction to higher order ingredients. Yeah. Any other question? Yes.
Sorry.
No, please.
If you introduce another length scale, say like from volume exclusion, I guess again not just complicate things, but it really affects this the top right.
So that's a very good question. So as I told you, for bacteria they live very low volume fraction, few percent. So pairwise forces are irrelevant. Of course, by the time you do this type of very dense patterns, particles have size, and then you can ask what happens. So we looked at that with a student, Quan Nguyen, who's shown that it's very rich what can happen. What can happen is, for instance, that these systems phase separate, so it makes this dense phase. And then within this dense phase, the pairwise forces trigger a secondary motility-induced phase separation. So you take this system which is dense, you add repulsive forces, it becomes even denser.
Because they slow down.
Because they slow down even further. And you can have the converse effect when, if this was going to crazy high density, then this could be arrested by the repulsive forces. So depending on the type of how the maximal packing fraction allowed. So what's interesting is that the MIPS with pairwise forces, the packing fraction is the relevant number, and here it's the number density. So depending on what is the limiting fraction, you get very interesting type of interaction, and this is something that should be coming up, within the next few weeks or something like that. Yes.
Is it clear that this activation or inhibition, so that you have a monotonicity in the beat, or it could be something?
No. So that's a good point. Definitely, you will always have inhibition at very large rho. So whenever you have activation, you should get afterwards inhibition. So when my students complain about the pace at which we write papers and get them submitted, I remind them that I have one paper which took 14 years to be published. And that's the one on measuring experimentally the motility of bacteria. It's amazingly difficult. So the data that biologists have on motility is is very limited. They know that bacteria have metabolic interactions. They produce lots of stuff, and they process them. Sometimes it helps, sometimes it doesn't. It's easy to grow them together and then to just count the number of bacteria. So looking at these reaction terms is easier, but the transport is horribly difficult. So one of the things that I would like people to do is to start doing this. So Lawrence Wilson, who's an expert in DDM, has kind of agreed to start and do a scattering of bacteria and put them together and look at whether they swim faster or slower. But there is very limited information. I mean, this is, it looks like a curve that physicists would not be very happy about, but the measurements that JD did here for motility, that's one of the only case I know of a quantitative measurement of variation of speed because of density. Another one is in the lab of Joshua Shevitz. They tracked bacteria when they enter this aggregate, and they showed that there is a slowdown of speed, but it's very difficult. And you're right that from the point of view of pattern formation, if you are low for non-motor stuff, you have really crazy things that can be possible. Okay, good. So, okay, yeah. Let me now move to the second topic of my lectures, which is collective motion. Okay. So we switch gear a little bit. What is collective motion? Collective motion is the ability of individuals to move coherently over scales much bigger than any microscopic scale. So typically the size of individuals or the distance between individuals. This is something that we know is seen at, in group of animals, but it's also seen at the microscopic scale. Here on the left, you have clusters of myxobacteria that swim together. It's also something you can see it with molecular motors. Here, that's these swimming colloids that I showed you on the first day, and I'll come back to them in a minute. These are experiments by vibrated discs by Olivier Dauchot, where again, the color code shows how aligned with your neighbors you are, and you see that they do these swirls in which they are very coherently moving together. So all these systems are very interesting for their own sake. And as statistical physicists, what we want to understand is what are the minimal ingredients that can lead to collective motion, and what type of phase transitions lead to this collective motion. So this is a question that 30 years old, which actually founded the field of active matter, when Vincek and co-workers said that this is surely a too complicated model, but maybe we can understand a simpler one, which would be the following. We take n self-propelled particles in 2D, in a continuous space, and we implement a local alignment rule, which is what we will call a metric rule, meaning that I take any particle, and I look at all other particles within a given distance, R0, that's why we call it metric. I compute their average orientation, and I align with this average orientation up to some noise. And then I step forward. Okay, so it's a little bit like ferromagnetism plus self-propulsion. Okay, so if you put that in a computer, what you get is what initially reported Vincek and co-workers. If your noise is large or your density is low, you're bad at aligning, you have nobody to align with, you're disordered. So you have random, all your particles do a random walk. If you have very low noise, you're good at aligning. If you have high density, you've got lots of people around you. You get a fluctuating floating state. And the big surprise at the time was that this state has long-range order in 2D. While if these particles were aligning and staying on place or just doing diffusion, Mermin-Wagner theorem would forbid the emergence of long-range order. So there was really a huge excitement about that. And Vincek and co-workers reported a critical transition between these two states. And then 10 years later, Hugues Chattet and Guillaume Grégoire showed that actually the transition is not first order, it's not second order, it's first order. And between this disordered phase and this fluctuating floating state, you have an inhomogeneous region with this dense band. Okay? So this is what happens in a computer. You could say that's very far from birds. Yes? Okay, so I would say discontinuous transition. Then I have an order parameter which I can define, and it jumps discontinuously. Anyway, it's a bad way of speaking about this system. I should really be speaking about phase separation, and I'll get there later on. I'm using the language that was used at the time. Yeah. If you were trying to think, if you were trying to think in terms of a ferromagnetic transition, you define an order parameter, which would be just the average orientation, 1 over n, the sum of the orientation. And if you were to go from here to here, you would see it varies continuously, and you would say it's a second order transition, okay, critical. And if you see it jumping discontinuously, you'd say it's a first order transition. But anyway, it's not a ferromagnetic transition, so we'll get back to that in a minute. Thanks for the question. So it's not just something that you see in silico, it's also something you can see in experiments. So Denis Barthelot has used what's called the Quincke effect to implement that in an experiment. So what is the Quincke effect? You take a fluid which is conducting, you apply an external electric field, and you put a small bead which is an insulator. So what happens is that because you have a field which is like that, you have your electric charges that goes up, they accumulate there, they are depleted here, and so you see that you have an electric moment that develops, which is opposite to the field. Because it's opposite to the field, it's unstable, it wants to rotate and align, and so it starts doing that, but there is a torque and there's a time scale for which to rotate, and before it can fully rotate, other charges have arrived, and so it's essentially stabilized at a constant angle with the bead continuously rotating. When this continuously rotating bead falls on an electrode, it becomes a wheel, and these guys are self-propelled. Now, when they swim around, they're charged, so there is electrostatic interactions. They're carrying fluid with them, so there is hydrodynamic interaction. And the result is that you can observe the traveling band predicted by, that's really annoying. Let me see, I'll switch gears. Oh, I don't have a killer, really. Let me see. What was your name? Quincke rollers. Okay. So these are colloids that are doing a random walk. So there is no, the electric field is normal to the plane. So their direction is not selected. And you see that because of the aligning interactions, you have this band which is coming and traveling to the left, which is very reminiscent of the band that I showed you before. And I hope that only the move file will be a problem. We'll see. Okay.
In the band before, there was phase separation. I mean, the band was on its own, and the rest was depleted. Here, would you?
Well, here before you had something. No, it was not depleted. It was dilute. Dilute. So if you want, here you have, these are your the colloids you saw at the beginning of the movie, the one that were dilute, and then you have the band which arrives. But we'll get back to the nature exact of these things. So if you increase the density, what the Vicek model would predict is that you should get a polar liquid. And I really hope you're not, oh no. See, PDF is not a norm because we should not be regulated. And as a result, it's a security hole. And instead of fixing that, people just forbid using it, which is OK. Let me see the Niband 1. That will be a long talk. OK, so higher density, you get a polar liquid. You see that everybody is uniformly is aligned and going together. That's my fluctuating flocking state. You can measure, and they are the same properties as the one. Now, if you go to even higher density, we go back to the previous part of my talks. Particles are not point like. They should interact together. And what I told you is that they should do MIPS. So, Denis Band 2. OK, so this is a much denser polar fluid. So here you have a very dense polar liquid that's flowing to the right, undergoing motility-induced phase separation, so doing an even denser phase. This is arrested. This is a traffic jam. And these are all the cars on the highway entering the traffic jam and the interface of the traffic jam going to the left. Because of mass conservation, the traffic jam has to dissolve. And at the other end of the traffic jam, you see the polar liquid that resumes. So you see that the Vicek model was predicting 3 phases. The experiments, of course, because it's in the real world, see something a bit nicer. And so here, this is a motility-induced phase separation, not between a gas and a dense phase, as in the first part of my talk, but it's a motility-induced phase separation between a polar liquid here and an arrested solid. So the 2 first lines correspond to the standard Vicek model, and this is beyond Vicek physics, just to show you that these things can happen. OK. So it's been 30 years that the Vicek model has been introduced, and it keeps giving. So there has been many fruitful debates. And the first one was on the nature of the long-range ordered phase. So Tailleur 2 in 1995 produced a theory that explained the existence of the long-range ordered phase, detailed in 1998. And then 2005, they said, no. We had written this phenomenological model to explain our system, but actually we forgot a term that was allowed by symmetry, which Sri Rama Maswamy noticed. So let's patch it. They did it, but then they realized in 2012 that actually, they still believe the long-range order is here, but actually, they were using exact symmetries to compute exponents, and actually the exact symmetries are violated, so it's a bit more complicated than that. But we still believe that long-range order exists. Then Mao and Chaté in 2019 do enormous simulations. They prove that Tailleur was right. There is a long-range order, but all the exponents of the theory are wrong. And this triggered again, a thread of theoretical papers, including some by Hugues Chaté and Alex Solon.
So Julien, when you say long-range order, you're speaking about the inhomogeneous phase or the
ordered phase. The ordered phase. Yeah. Polar liquid. Yeah, the polar liquid, the fluctuating flocking state. The one that, if it was an XY model, would not have long-range order, would have quasi-long-range order, and here has long-range order. So the simulations say long-range order is fine, the exponents are different. Chaté and Solon have produced a theory that predicts these exponents, but it's not exact. There are some hypotheses. And that triggered a nice debate. So March 2025, the inconvenient truth about flux, which essentially says, oh, this theory has to be wrong. And then a comment on the inconvenient truth about flux. And then a response to the comment on the inconvenient truth about flux. No, we're in May, okay? And then continuing the discussion on the, so I will not enter that debate. I invite you to read these papers. I like a lot the one by Châté and so on, which I find very easy to understand. There is a starting hypothesis, and there is a question about whether it's right or not, but at least it produces exponents compatible with the numerics, which was not the case before. So that's the first debate, but that's not the only debate. Then there was a debate on the nature of transition. Witczek 95, continuous transition. Châté 2004, discontinuous transition. Châté 2010, if you have topologic interactions on metric, continuous transition. US 2013, it's not a ferromagnetic transition, it's liquid-gas transition. I forgot a paper in 2015, which is it's not phase separation, it's microphase separation. Then us again in 2021, actually the topological papers, the topological models are also first order. Okay, so complicated. And then 2022, 2022, forget about it. Actually, the ordered phase is not stable. All you're doing are weird small fluctuations. This is metastable. If you nucleate a small default, which is dense enough, this is what happens. So here the black phase, this is an ordered phase in which we are inserting a small defect. Okay? The probability of nucleating this defect is rare because it's dense, but and this is what happens. The defects, instead of shrinking, as surface tension would do to make this phase stable, grows ballistically over time and will flip the full side. Which means that if I have an infinite system, my probability of nucleating this defect somewhere is 1. And everything I'm going to tell you about the activating model having an ordered phase is wrong, because asymptotically, you'll never see it.
So what is the nature of the defect?
Exactly. So it's just dense. It's just a disk with particles which are opposite. I will get back to that at the end of, hopefully. But essentially, so here you have a background of density rho naught. You take a disk of density 3 rho naught, you flip it, you flip the magnetization, and you just let it propagate.
But if you have Ising model with two symmetric faces, you would get also.
No.
I mean, you can have.
If I take Ising model with plus m, I take a disk, I flip to minus m, I have surface tension.
Yes, but what I'm saying is that you have a symmetry, so it might come. I mean, flipping from one state to another could be this.
But you will no. Okay, so here I'm nucleating a microscopic defect and it grows. Yes. That would never happen in the Ising model. If I nucleate a defect, it shrinks because of surface tension. So if I have, then what I can do is I can wait, and then my full phase flips. And that takes a time that diverges exponentially with the system size. Here, the time it takes decreases as a power law with the system size. So it's scaled, the tau decays as 1 over L to the D instead of increasing as exponential L. That's the big difference. So thermodynamically, it's not stable.
But again, so you are here in the polar liquid, and you put a defect which is more.
I take a circle which has 50 sides, and I flip the magnetization, and I increase a bit the density. Okay. And I wait, and I run my simulation.
And then you see.
And Asterix takes over the Roman Empire.
Sorry, Julien.
Yes.
Sorry, but then what is the steady state? Because you can put many.
The steady state would be a chaos of droplets that goes back and forth in all directions. Yeah, that's what we believe. But of course, this simulation is very difficult to do. So getting to this steady state, we will need to find models in which this happens on a faster timescale to be able to do that. Okay, so and there are many more open questions. So today, essentially, what I will focus on is what I understand best, which is the nature of the transition and where there are kind of solidly established results. There are less, it's less a frontier for the field right now. Okay, so historically, 2 scenarios have been put forward for transition to collective motion. The first one is a discontinuous transition, or called first-order transition. And a representative model in this class is the metric Witczek model, as I showed you, because of these bands. And they are both numerical results which are convincing. And if you do a mean field theory of the Witczek model using Boltzmann kind of approach, like Eric Bertin did, you get that analytically. It's until 11, right?
Yes,
Yeah,
yes,
good.
20
I see that my chairman is already bored.
Give the time to explain.
No, there is a second scenario which has been put forward, which is that of continuous transition. So continuous transitions have been predicted in scaling limits of metric models. So there are lots of work by Pierre Degon and co-workers in which you work into some limit where you can do something analytically, and then what you get is allegedly a continuous transition. Closer to physics, there are also what people call topological models, which are allegedly supposed to represent what animals or cells do. So one example can be, imagine you have a tissue. So each of these Voronoi cells represent a cell in your tissue, and you align with your neighbors. So it's not a question of distance; it's a question of who are your Voronoi neighbors. I don't like calling them topological because if you change metric, you change your neighbors, but that's a detail. Another type of model which has been looked by the people in Roma a lot are the k-nearest neighbors, because birds apparently align with up to 6 neighbors next to them. And in this class, there are numerical and analytical mean field results that strongly suggest that the transition should be continuous. And what I would like to do today is I want to characterize the first order transition to be a bit more precise about what I mean by that. And then I will review a mechanism that actually rules out this continuous transition, or at least say that if it exists, it is fragile. And I will argue that the fluctuations make the mechanism of this continuous transition generic. And to do that, I will use another model, which we introduced with Alex Solon in 2013, which is the active Ising model. And it's a nice model because if you do numerics, it's very simple, and you see first-order transition. If you do analytics mean field, it's very simple, and you get continuous. So clearly, there is something wrong in this mean field computation. And I will show that there is a fluctuation-induced first-order transition, so that mean field miss it, but you can patch it. OK, so why do we go from birds to flying spin? And how did I get to work on the active Ising model? When I was a PhD student, 24, 27, I heard many talks from Hugues on flocking, and I thought the VCheck model is horrible. Continuous time, continuous space, discrete time, n-body interactions, collisions. I don't know how to deal with that. I'll never work on this. Lectures by John Tanner, okay, very complicated phenomenological equations, very easy to miss terms. But there was something that was kind of bugging me, which is the title of John's seminal paper, where he says long-range order in a two-dimensional dynamical XY model. And if you think about it, the VCheck model is very far from an XY model. It's not on lattice, it's not, it's a many body interactions, it's discrete time. And so I kept thinking, but why don't we try to do a flying XY model? And when Alex Solon joined my group, I told him, why don't you do that? And he told me after a few days, I have no clue how to do even a flying Ising model. And so I said, oh, let's start with a flying Ising model. So how do we do a flying Ising model? So we want to take Ising model and make the particle move. If the particle move, we have to allow for several particles per site. Okay, so the idea is that on each site, you have ni plus particles with +1 spin, ni minus particles with -1 spin. You can define local density and magnetization. And I want both alignment, because I want an Ising model, and I want propulsion. So we thought we were being clever by saying, let's do on-site alignment. Okay, on each site, we put a fully connected model, a fully connected Ising model. Why do we do that? Because we know that at large density, fully connected Ising is mean field. So we will have a very easy way to do the theory of this model, which is to work at high density and do mean field. Okay, so on each site we have these flipping rates that are the standard, that satisfy detail balance with the standard Hamiltonian of a fully connected Ising model. We have some temperature that controls the alignment strength. And then we have to do self-propulsion. And so essentially what we say is that our particles have scalar spins, so we can bias direction in one direction. The plus spins go to the right, the minus spins go to the left. And of course, because we need to mix our system, we also had symmetric hops at rate d in all directions. Okay? So we have a lattice on each side, fully connecting Ising model, random walks, plus a biased random walk, so the plus go to the right and the minus go to the left.
And this 1D.
This is 2D. You can do it 1D if you want, you can, but it's hard, yeah, you can do it any dimension you want. So this is a standard snapshot in a 2D system. Here the color code is the magnetization. Essentially, so the plus spins go to the right, the minus spins go to the left. Because the system is just doing diffusion along y, it's invariant by translation along y. So when I'm plotting profile here, I'm averaging along the y direction and plotting along x. This is my temperature density phase diagram. You see that at small density, large temperature, I have what I call a disordered gas. So my density is homogeneous and constant. My magnetization is homogeneous and 0. Okay, disordered gas, boring. I go at low temperature, high density. This time I have what I would call an ordered liquid. I have a homogeneous density and I have an homogeneous magnetization, which is here very close to the density. And in between, like in the Vicek model, I see this big liquid band, which is propagating. And so if I look at what this guy is, I have a coexistence between here, a disordered gas, homogeneous, disordered, and an ordered liquid, homogeneous, ordered, and an interface in between. To get a feeling of what happens in this system, if my computer allows me, yes. Okay, it's just discriminating against Mac movie, so it's fine. If I start from an ordered phase, and I increase the temperature to go in the coexisting phase, I get an instability. So here the color code is the magnetization. So white means disordered, so there are particles, just don't see them. And as time goes up, I see that I have a number of bands that form, and you see that there is a coarsening process in which the big bands eat the small band. And at the end of my simulation, which will take some time, the big band has eaten the small band, and this will come back later on, and I have a single macroscopic band that will relax towards something straight. Okay, instead of starting from an ordered configuration, I can start from a disordered configuration. Again, an initial instability leads to clusters. This time I have plus clusters that go to the right, minus clusters that go to the left. I speed up my simulation so that you can see the full coarsening. At some point, I have just two bands remaining. These bands, essentially, when they meet here, they fight when they touch. See here, tack, tack, stealing particles from each other. Now is a good time to make a bet about who will win. Green, pink, pink. Okay. Of course, it's an ergodic system. You have the same steady state. If you're an experimentalist, you may be uncomfortable with periodic boundary condition. You can put it in the box, and then you just have the bands that bounce back and forth. Whatever boundary condition you put, you get the same thing. Closed, reflecting, doesn't really matter. Okay. So that's the physics of this system. And if you try to do the standard finite size scaling for ferromagnetic transition in this system, you fail miserably. And the reason is that actually this is not a ferromagnetic transition, it's a liquid gas transition. So to see that, what you can do is you can work at finite temperature, and you can ramp up and down the density. And this is what you see. Here you have the fraction of liquid. So you start in the gas phase. You have 0, 0, 0, 0, 0, 0, and at some point, bloop, you nucleate a droplet. That's this blue droplet. As you keep increasing the density, what happens is simply the droplet spreads, and there is a Lover rule, so the density doesn't vary, just you're changing the weights of droplet, until you almost fit your droplet in the system, and then boom, you're in the liquid phase. When you go back, you enter the binodal region, but not the spinodal, so you're metastable, and then at some point, bloop, you nucleate your droplet, and then you go back down. And this is exactly what you would see if you had an equilibrium liquid gas system and you were varying the density at fixed temperature. And if you try to look at this transition not as ferromagnetic but as a liquid gas, then everything fine and all your finite size scaling works. And in this sense, I'm speaking about first order transition just because it's the analogous of phase separation in equilibrium. But I agree that there is no free energy, and so this is a debatable question. Okay, you can also look at the phase diagram in the density speed plane. So I was showing you result of simulations for v equal 1. Now, when v is equal to 0, you don't have an Ising model. You're not in equilibrium because the hopping is insensitive to the energy, only the alignment is. But nevertheless, you can show that the critical point is in Ising universality class. Okay. So first take-home message. The flocking transition is a liquid-gas transition in the canonical ensemble. And it leads to an ordered liquid instead of a disordered liquid. This has big consequences. In equilibrium, you know that this is your phase diagram. And you can continuously go from a disordered gas to an ordered liquid by going around the critical point and going to the supercritical region. Here you can't because the gas and the liquid have different symmetries. So you have to cross the transition line, and the trick that nature has found was to take this critical point and send it to infinity. And so that's why you get this crescent-shaped phase diagram. This is true for active Ising model. It will be true for Vicek, active nematics. This is very general, just a symmetry-based argument. So what I want to understand next is what prevents a continuous transition and what selects the nature of the coexistence phase. And because I have 8 minutes left, I will not go on the blackboard. I will do it with the slides. And I will go to the blackboard this afternoon. So the first thing you can do is you can try to do mean field. We did this model because we thought mean field would be good. So again, you have your density field, your magnetization field. You can write down equation for the average density and the average magnetization. You do mean field, meaning that the average of functions of rho and m are replaced by the function of the average. You do a gradient expansion, and this is the term you get. So you have, random hopping on your lattice that will give you diffusion. And I don't know why these are x, so this is 1D, but okay, that should be a Laplacian. You have self-propulsion only along x, so these terms are only along x, and they're advective terms. And you have an alignment which is on side, so you get the standard expression that you would get for your mean field theory of fully connected Ising model. Okay, so you have these equations, and you can analyze them, and you can look at whether you can understand your phase diagram. So what you do is you look close to the onset of order, so you expand your fields for m equal rho being small. And what you get is something that looks like that. So again, diffusion, advection, and alignment. And this is your phase diagram when this coefficient alpha changes sign. So if alpha is positive, you have m dot equal minus alpha m, which brings you back to m equals 0. So you have a homogeneous disordered phase, which is linearly stable. When alpha is negative, instead, m equals 0 becomes unstable, but you have the m cubed term that balance. And what you find is a homogeneous ordered solution, okay, which with m is square root of minus alpha over gamma. And this is again linearly stable. And this is very sad because it means that the mean field treatment predicts a continuous transition. You can also show that traveling band solutions are ruled out. So that just mean field is wrong. So what is mean field missing? We know it since the work of Eric Bertin in 29. It's the fact that this number alpha here, which when you do mean field is just 2 minus 2 beta, so that the critical temperature is the mean field critical temperature T equal 1. This is a constant. And we know that in the Vicek model, for instance, the first order transition comes from having alpha of rho. So indeed, if instead I had obtained an alpha that depends on the density, then my homogeneous ordered solution would be linearly unstable close to alpha equals 0, and instead of having this phase diagram, I would predict that phase diagram. So in the last few minutes, what I want to show you is why this coefficient indeed makes the homogeneous ordered band linearly unstable. There is a simple mechanism that you can understand. And this afternoon, what I will do is I will take this equation, and I will say that mean field has forgotten some noise here, and so I should add this noise and compute again the harmonic equation. And I will show you that this renormalize this coefficient, make it density dependence, and induce a first order transition. Okay. So let's start by just the instability mechanism. How can we understand that just having a density dependent critical temperature Alpha here is proportional to T minus Tc. So why does a density-dependent critical temperature leads to a first-order transition? I can look at a very minimal model in which my density is advected by magnetization, and my magnetization is simply doing aligning dynamics. Okay, that's all I put in the system. Again, I do the same game as the one I played with MIPS. I start with a system which is homogeneous at some magnetization M naught, which is given by this number here, and I add a perturbation. Okay? Because rho dot is advected by M, the derivative of sine is a cos. So what I will have is that there will be an out-of-phase response of rho dot. Rho dot will increase in this part between the maximum and the minimum, and it will decrease between the minimum and the maximum. Okay, so I get this guy. But now, because rho has varied, alpha of rho will vary. Because alpha of rho varies, M will vary. So I have to make a decision. And for now, I take alpha prime negative, so that M is an increasing function of rho. M being an increasing function of rho means that in this phase here, my magnetization profile has to go up. In this phase there, it has to go down. And then, at a linear level, I want this to relax towards a new profile, which is another sign. One thing that you notice is that this point haven't changed here, and I need to draw a new profile. So I have no choice but to draw a profile which has a higher amplitude. And so my new perturbation has a scale which is larger than the previous one. And so the fluctuations of T minus Tc amplifies delta M. So what's the mechanism? The mechanism is that the density-dependent critical temperature prevents the continuous transition. How? Fluctuations of M advects and creates fluctuation of rho. In turn, the fluctuation of rho creates fluctuation of the critical temperature. That creates fluctuation of order, which amplifies the initial perturbation. Here I took alpha prime negative, and you see that my perturbation moves to the right. If I had taken alpha prime negative, the arrows would be downward, and my profile would be moving leftward. But that's the only difference. And so that should be generic. And so this afternoon, we will see, OK, so still 2 minutes, so let's use it. So let me just show you that this is indeed a solution to the problem. So as I told you, the active-phasing model mean field is wrong in all ways. The phase diagram is wrong, the order of transition is wrong, and there are no bands. But I told you if you just correct my linear term, it will be fine. Now, as I told you in this model, mean field, I expect it to work fine because I have fully connected Ising model. So if I send the density to infinity, I have mean field. But if my density is finite, I should expect corrections in 1 over rho. So what I could say is this 1 is not 1. It's 1 plus r over rho. Now I can take this model and put it in a computer. If I do, that's the phase diagram I get. Instead of having this mean field critical temperature at 1, I get this crescent-shaped phase diagram, which is the good phase diagram. And I get all the same phenomenology as the microscopic model with these, both the linear instabilities, the phase coexistence line, the liquid gas nature, the hysteresis loops, blah, 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 everything. OK, so what I will show you this afternoon is that this scenario in which you get this density-dependent critical temperature is generic. I'll do that analytically on the board. Then we'll go back to V-check model, show that the same phenomenology applies. We will go to the topological model that were claimed to be continuous. And I will show again that no, the transition is not continuous, it's first order. And then we'll discuss how we can understand the shape of these bands by solving a nonlinear mechanics problem. Thanks for your attention, and if you have any question. Yes?
So the definition of the model, you chose the rate to be e to the minus beta m over rho.
Yes.
So that's a choice. You could also have e to the minus beta m if you imagine particles applying torques on each other additively, right? So would that automatically give you alpha of rho? Because that's like beta of rho.
It does, but that model, so it does, and we did that in a paper with Fred Farrell and Davide Marenduzzo in 2012. I was very happy of this paper for that reason. Turns out that this is a very pathological model, because the denser your band, the more aligned it becomes. And so initially you take a system size, given system size, you simulate it, you get your phase separation. If you increase the system size, at some point your bands becomes unstable. So the fact that you are, so in a way, and it's not completely surprising, because from the point of view of the Ising model, you're doing a fully connected Ising model without the 1/n. So your energy is not intensive. So by just packing up density, you get singularities and problems. So
it's unstable in what sense? So what happens? It gets denser?
That's a very good question. Nobody has published any result on that. So in my case, what I saw was that I had clumps. Instead of getting bands, the bands break into clusters. There is a PhD student of Mike Cates, whose thesis is published, who saw another type of symmetries in which the band was kind of having transversal instabilities. But this is, this is a pathological model, so it's very hard to do large N systems. So you just know that, okay, something wrong is happening, but we don't really know what. But yes, so here, the mean field is wrong because of the choice I made, believing I was being smart, and actually was making my life a misery. Yes?
Is it possible to have limit cycle solutions for magnetization in such system?
So you mean fluctuation? So yeah. So okay. In the periodic way, I don't think I've seen it. You can get chaotic dynamics. So if you take instead of doing polar system in which you have a polar alignment, you take nematic alignment. You see a band, but in large enough system, this band destabilizes, and then you get a chaotic dynamics. I don't see anything that rolls out. The period, I mean, by changing the model immediately, but I'm not aware of anybody having seen that right now. I'll think about it. Good question.
Yes. I'm still curious about what you said about the instability of the order phase.
Yes.
The Vichek model. So if the order phase is unstable, then the transition, I mean, so what is the status of the transition?
Okay.
There's a transition to what?
Yeah, exactly. So,
and also why, yeah, exactly, I imagine this came as a surprise, but if it's unstable, one would think that coming from the disorder phase, I mean, why coming from the disorder phase?
Okay. Because because it was difficult to see.
So just one question before. Yeah. In the other model, the Ising one is stable.
No, that's the other way around. It's even weirder. So let me tell you about it. So the way we came about it is that we did this work on MIPS, that you add disorder to MIPS and you destroy MIPS. And so we wanted to see what happens when you add disorder to Vichek. And we started to do what happens when you add disorder to MIPS, but then what you should do is just add one obstacle. And that's it. And then what we realized that a single obstacle destroys the ordered phase. That's the work of Yariv Kafri mostly was driving this work. And so then they realized that actually you don't need the obstacle. So what they did, so the numerics here from Sung and Ro, is you take your model, in the active Ising model, you have your ordered phase, you add a small defect, and either your defect disappears and you're stable, or it grows and you're unstable. You look at the probability of reverting the phase as function of the size of the initial defect, and you see that very small defect, nothing happens, and then above a given size, you go to probability 1, and this is independent of the full system size. That's the picture I showed you, that this thing is growing. If you look at the time the system survives as function of the system size, you see that it indeed, the nucleation rate scale as to the D, and so the survival time decays as 1 over LD. So this is a numerical result that super difficult to get, and that you can get in the very specific corner of the parameter space. You still have to nucleate these defects, and they are not that small. Tenside that spontaneously flips. If you were trying to do that in the region of the parameter space that I showed you, these numbers would be 10 to the 30, 10 to the 50. And so essentially, when you simulate active Ising model, you don't see it. In the experiments of Denis Barthelot, it should be there, you don't see it, just because the system is too small. So it's just very difficult. One thing, because Sungan made this beautiful movie, so I should show it. It also happens in 3D, so it's not a 2D effect. Here you don't see the backflow, but there is a backflow of particles with negative magnetization, and you only see the growing comet of positive particles, and again, this guy will take over. So it's well known in equilibrium physics that continuous order parameter is more fragile than discrete order parameter. So we thought if active Ising model is fragile, then Vichek model is dead. Turns out it's the other way around. So, and these are results we are writing right now. So what makes these grow is that the domain wall here, which is at the front, is very solid. So this domain wall is robust. And when you go from discrete to continuous, the domain wall, because of the spin wave, becomes fragile. And the region of parameter space in which this is growing becomes much lower. So in the case of the V-check model, I will show you this afternoon the phase diagram, which is here. So that's the phase diagram of the V-check model. You have the gas plus band, and band. Essentially here, close to this region, there is a line where the system is not stable. At low density, same thing, the system is not stable, but in the middle here, there is a lump, which is infinite, so it's not small, in which the ordered phase is stable. So in the case of the active Ising model, the ordered phase is not what we believed it was. Now, asymptotically, it would be this kind of back and forth comets that are going. In the V-check model, there is a fourth phase, until we discover the fifth phase. Any other question?
Okay, so maybe we can start the break of 30 minutes. 20 minutes. So we are back at 11.